Hello everyone, welcome to Tanisha's Concept Corner. I'll be teaching math, chemistry, and physics portions for the 12th grade. So let us do physics today, chapter 9, ray optics and optical instruments. This is from the part 2 book. So there is an introduction given over here. Let's go through it. So we know that human eye has a part called retina and it is sensitive to the electromagnetic waves. Nothing but light is an electromagnetic wave. You know that electromagnetic wave doesn't need any medium to travel and it can travel in vacuum. And electromagnetic radiation is like a wide spectrum of different wavelengths and frequencies. So if you see over here, there is a huge range of this wavelength. But if you see the wavelength range from 400 nanometer to 750 nanometer, that is called the visible region, nothing but light, the visible light that we are able to see. Whenever this electromagnetic wave is having this particular range of wavelength, then only we are able to see it. But other rays like X-rays, gamma rays, infrared, microwaves, these we cannot see with our naked eye. And light is nothing but a form of energy which enables us to see. That is what this para is telling about. Then, two things we can get to know about light is from common experience. One thing is that it travels with enormous speed, and second thing that it travels in a straight line. If we have experienced light, we can get to know about these things automatically, because whenever you're turning on light, you're seeing how quick it is, how fastly it is traveling, and also it travels in a straight line. Shadows, if you're putting some of the object some of the other object in front of light, you can see that there is a shadow that is formed on either the wall in the front or any other plane surface that you have kept in the front. That means light rays are traveling in a straight path and some obstacle is there in the middle, so shadow is formed. So this we got to know, and then it took some time for people to realize that speed of light is finite and measurable. Because the light travels so quickly, people thought that okay, it may not be finite, we won't be able to measure it. But there was a way to measure it, and we found out that speed of light in case of vacuum is 2.99792458 into 10 power 8 meter per second. Obviously, we can't use this much huge values for the calculation, so we rounded it off to 3 into 10 power 8 meter per second. And speed of light in case of vacuum is the highest speed that can be achieved in the nature. Now, we already know that light is traveling in the straight line. And it's traveling as if like from one point to another, it is joining the line. So if you see, this is called the ray of light. So whenever light is traveling in straight path, it is as if it is joining the 2 points in a plane. So this is called the ray of light, and if you see bundle of those ray of light, this is called beam of light. And we will be using these concepts in order to know about various phenomena of reflection, refraction, dispersion further in this chapter. So first, reflection of light by spherical mirrors. So to understand this, first we can see the normal reflection in case of a plane surface. So what will happen? Incident ray will come and then it is bouncing back and giving a reflected ray. That is what is reflection. Reflection is nothing but bouncing back of light rays into the same medium. If it is going into another medium, that will be called as refraction. So bouncing back of light rays back into the same medium is reflection. And if you see a plane surface, incident rays there, reflected rays there, you have drawn the normal. This angle to the left is angle of incidence and to the right is angle of reflection. So we know the laws of reflection, saying that the normal, incident ray, reflected ray at the point of incidence all will lie in the same plane. In this plane only they are going to be there. If this is the monitor, in this plane only they will be there. They will not be coming out of the monitor. That is what it means if they're in the same plane. And one more thing, we know this angle of incidence is equal to angle of reflection. This if there is a plane surface. What will happen if there is a spherical surface? When spherical surface is there, like the curved surface, you get a mirror. You get two kinds of mirrors, concave and convex mirror, which we will discuss in further. So over there, normal will be normal to the tangent to the surface at the point of incidence. Now over here, normal you can directly draw because there is this plane horizontal surface over here. But in case of a spherical surface, you cannot just directly draw the normal because it's like circular. So generally, whenever we are facing that issues, whenever circularly, if there is a surface and you're facing such issues, you always introduce a tangent. So normal to the tangent you can draw, and then generally that normal will go along the center of curvature. So if you see over here, to understand concave and convex mirror. So this is concave mirror. Remember cave, like inside, the inwards part. Concave mirror. So there is pole. This is nothing but the geometric center, that is called the pole. And center of curvature, then generally this is the spherical in form. And you are taking this part to make a concave mirror. So that center of this entire spherical shape is the center of curvature. And if you're going to join a line from center of curvature to pole, that will be your principal axis, and between this you get something called as principal focus over here, where all the rays are going to converge. We will discuss about that. Aperture, you can think it like a diameter of this, and radius of curvature will be the distance between C and this spherical surface, the concave mirror. So if you see the spoon, the curved inside part, concave part this is, and you get generally like a inverted image over here, and convex part will be bulging out like this. So the bulged part is over here. This light green color is showing where it is actually polished. So the reflection takes place at this bulging part. And same thing, center part will be pole. For geometric center of this mirror will be the pole, and entire spherical form in between that center, what is there, that is center of curvature, and distance between these two is radius of curvature, and the line joining these, it's like an imaginary line, that is principal axis. Aperture is like a diameter. So this bulging out part, if you see the spoon, if you turn it back, this is the bulging part, and you get a virtual and erect image. Real and inverted image. Inverted meaning you will get it ulta. You will get it upside down. Erect meaning it is straight. Generally in plane mirror, normal mirror that we use also, that will give you erect form, meaning straight forward. So real image is something that you can catch on a screen, but virtual image you cannot. So when some reflection is happening here and some image is forming, if I hold like a screen over here, if I'm able to capture that image on the screen, the paper, that whatever I'm holding over here, that will be real image. But if I'm unable to get it, that means that will be virtual image. So we will discuss about it also. Now we are saying that normal, if you have to draw, how you will draw? You will draw it through the center of curvature. So let me show you. If you have to draw normal, first there is like a incident ray. For suppose the ray is coming like this, always show the arrows, and suppose it got reflected back like this. Now if you want to get angle of incidence and angle of reflection, you need normal. So through center of curvature you're going to draw. Generally you can put a tangent over here like this, and you can draw the normal like this. So between the normal and the incident ray, whatever angle is there, that is angle of incidence, and between the normal and the reflected ray, whatever is there, that is the angle of reflection. And same rules will apply over here also. Incident ray, normal, reflected ray, all should be in the same plane, and incidence, angle of incidence should be equal to angle of reflection. That is what they're saying over here. For a spherical surface, generally you can draw normal, that is this normal, and this is entirely to the tangent, meaning this will be 90 degree, because it's normal meaning it's 90 degree. So you can draw tangent to make it like appear like a plane surface, and then you can, it will be along the radius, because you're passing it through the center of curvature to the mirror. So whenever there is this center of curvature to the mirror, then that will be called as radius only, radius of curvature, just like a circle from center to anywhere at the border. If you draw, that will be considered as radius. So along the radius you can draw through the center of curvature, and then you can mark the angle of incidence and angle of reflection. So this is what reflection of light by spherical mirrors is about. And as I already told, geometric center is called the pole, and in case of lens you call it as optical center. And the line that is joining the pole and the center of curvature is called the principal axis, the imaginary line that is going to join the center of curvature and the pole. Then in case of the lenses, what will happen? The principal axis will be joining the optical center with the principal focus, which we will be seeing later on. Now, most important thing while solving numericals also is sign convention. So this sign convention is like general Cartesian sign convention only. The Cartesian sign convention is nothing but that we used in our mathematics. So we generally plot this as x-axis, this will be our y-axis, and this x used to be over here. In case of this used to be positive and this used to be negative. Similarly for y-axis, this used to be positive, this used to be negative. So that only we are following over here. Generally, whenever we want to measure any sorts of distance, like generally object can be kept over here. If object is kept over here, you want to measure the object distance, always take it from the pole. Always measure from the pole, either to the left or towards the right. So generally wherever incident light is going, based on that our signs can be for object distance and the image distance. The incident light is in this direction. So if I'm going to measure my distance also in this direction, that means some image is forming over here. Then image distance I have to measure from the pole. Then I will measure it in this direction. Then that will become positive. But if I'm measuring it against, suppose some object is kept over here, instant light is coming like this, I'm measuring it like this because I have to measure always from the pole. Then I'm going against the direction of this, then that will be taken as negative. Similarly, this is nothing but x-axis, like think this as positive x-axis, negative x-axis. Then height upwards will be like positive y-axis, so it is positive. And downwards, if it is inverted, then you will consider it as negative, like negative y-axis. So this is what commonly we have accepted, and we will be using these sign for solving the numericals. Now the focal length. So principal focus, as I already told, generally it will be between this center of curvature and the pole, somewhere just right between these it will be, so that this distance and this distance will be equal. That will be principal focus. Whenever there is a parallel beam of light incident, paraxial rays is nothing but those rays which are going to be very near the pole. So you will consider these rays are very near the pole, so that they will make like a very smaller angle with the principal axis. Suppose if I take something like this. Paraxial rays are those rays where they're going to be very near the pole, generally the incident ray, and it will form very small angle with the principal axis. Those are called the paraxial rays. So when paraxial rays, like parallel beam of light is just coming, suppose if you take on a concave mirror, they'll all get reflected and converge at one particular point. That will be called as principal focus. The reflected rays will converge at one particular point, that is principal focus. This is in kind of a concave mirror. But if it is a convex mirror, the reflected rays will appear to diverge from a point. Now converging is generally when they're all like after reflection, they're meeting at this one particular point. For this, you have to know the general rule. That general rules are given over here. Actually, we studied in the 10th, but let me just quickly revise them. So for concave mirror, generally parallel beam of light we are saying, that's why. So whenever there is parallel light ray parallel to this principal axis, they'll always pass through focus. And if they're passing through focus, they'll always come parallel. This is the reflected ray, this is the incident ray. Follow the arrows. So this is the incident ray. Because it's parallel, after reflection it is passing through focus. This is the incident ray. Because it's passing through focus, then it will come as parallel. If it is passing through center of curvature, no deviation at all. It will just get reflected back in the same path. And if it just some angle near the pole it is coming, now this principal axis will nothing but act like normal over here. So this angle only should come over here. Like that it will get reflected. So that angle of incidence should be equal to angle of reflection. Same in convex mirror also, slightly different. The bulged part should be where your reflection is taking. Over here, the inwards part is reflection. In case of convex mirror, the bulging part. So this is like the behind the mirror. Over here, center of curvature, pole, focus, all these are towards the left side, and these things are not like behind the mirror. This is where reflection is taking place, so this is front. But over here, this is where reflection is taking place. Behind that is where your center of curvature and focus will be. So if suppose parallel some ray is coming, it should get reflected back through focus. But just don't draw it like this. That is a mistake, because it should get reflected back into the front of the mirror. It should not go completely behind the mirror. So you can just draw dotted lines. Whenever you're representing a ray from behind the mirror, you will draw dotted lines, and this can be normal solid line again. And if some incident ray is coming like this, that means almost like through the focus, then it should come parallel. Passing through the center of curvature should go back in the same path. Some angle or the other it is forming near the pole, from with that angle only it should get reflected back. So over here, if you see, in concave mirror, actually if many parallel beam of light rays are just coming, over here also one light ray is there, over here also one light ray, over here also one light ray, what will happen? They all, after getting reflected, should pass through focus only. So they will pass through focus. Here also it will pass through focus. Here also it will pass through focus. So all the rays are converging at one point. That is principal focus. For concave mirror, this definition will work. But for convex mirror, they are appearing to diverge from a point called principal focus. Like, what does that mean? So many parallel rays are there, suppose. Now they have to get reflected back through focus. So you can draw like this. Through focus, they have to get reflected back like this. So they are appearing to diverge from a point. From one point, if those rays, from one point, if those rays are gonna come in different directions like this, you call this as diverging. But to this point, all the other rays are coming and meeting. Look at the arrows. Then this is converging. And here you're calling it as appearing to diverge, because this is actually behind the mirror, and that's why we are representing it as dotted lines. So they're appearing to, you're not exactly able to see because you're in the front of the mirror. So because you're unable to see it, you're just saying they're appearing to diverge from one point. Diverging means from there all the rays are coming out. Converging is in case of a concave mirror, where you're able to see all the rays are meeting at one point. They're coming towards one point. So that is what they're defining principal focus as. And between this principal focus and pole, whatever distance is there, that is called as focal length. Yeah, same thing. So many parallel rays are coming and they have to pass through the focus according to the rule. So they're converging at a point in case of concave mirror, and in case of convex mirror, they are appearing to diverge from this point. And focal plane is generally where this is all taking place, like a plane that is passing through focus and is perpendicular to the principal axis, where generally all this incident rays coming and reflection is happening. That plane is called as focal plane. Now see over here, from center of curvature you have drawn. This is nothing but normal to get the angle of incidence and angle of reflection. So this was about it. Now there is a derivation saying that what is the actual relation between radius of curvature and focal length. Before that, here focal length of the mirror will be between principal focus and the pole, between principal focus and the pole, and FP will be equal to CP. F is the midpoint of C and P. Now so we will do this derivation. Actually, one more thing I wanted to tell is that whenever these reflected rays are meeting at one point, or they're appearing to meet at one point, that place only image will be formed. Because here it's happening in front of the mirror, and this is the solid lines that we have drawn, this will be called as real image. But over here they're appearing to come from this point, they're appearing to meet over here, then you will tell that as virtual image. So virtual image is formed behind the mirror, and real image is in the front of the mirror. So that is one more point. Now let us do the derivation. So how are we drawing? Okay, we have taken a concave mirror and plotting it with, suppose this is the geometric center, you have named it P, pole, then center of curvature and principal focus. Now you have drawn a perpendicular over here saying D and name this M. Incident ray is coming, and if it is parallel, it should pass through focus. Now this center of curvature, I'm just drawing the normal. So angle of incidence, angle of reflection will be equal. Now both are theta because both are equal. Now this is also theta. How come this is theta? We already know that this is parallel. If these both are parallel, these will become alternate interior angles. One such technique to find that will be Z. If you're getting confused how they're alternate interior or alternate exterior angles, when there is like two parallel rays, like any sorts of like Z or N you're able to see, those angles will be equal. Without you getting confused, you can think it in this way, or it can be like this also. So this, because if you're just gonna extend it, you're able to see both are parallel, this will be alternate interior angles. So here also you can see this is Z, this line, then this line, and then the principal axis. So these both angles should be same. So this is also theta. Similarly here also, again this line, and this line. So this entire angle should be equal over here because these are 2 times theta. So over here 2 theta is written. So you can tell the introduction saying that we took a concave mirror and this is the center of curvature and this is the principal focus, incident ray, light coming parallel. You have to write that in the introduction part and then we can start. So they have told MCP is theta, then MFP is 2 theta. So what will be tan theta? Tan theta is opposite divided by adjacent. So opposite is MD, adjacent is CD. Consider CMD triangle over here. And consider this theta at the angle C. So MD by CD. Then tan 2 theta will be, consider this FMD. So if you take tan 2 theta, it will be opposite by adjacent. That will be MD divided by FD. Now, these are small theta. You can again say that these are paraxial rays. Suppose they are very near the pole, they'll form very small angles. So, if there is any small angle, you can approximate tan theta as theta and tan 2 theta as 2 theta. If you take very small values like 1 degree, 2 degree, tan 1 degree, tan 2 degree will be approximately equal to 1 degree and 2 degree only. If you want, you can check in the calculators. So, if theta is really small, you can directly approximate it as tan theta will be approximated as theta. So we can say theta is equal to MD upon CD and 2 theta is equal to MD upon FD instead of tan. Now what they have done over here is, let me see. So try to understand in this way. So here theta is there, I'm sending 2 over here, then it will become 1 by 2 because it's in multiplication, it becomes into division. So take away this 2. So over here theta will be equal to half MD upon FD. So theta and theta, if RHS is equal, I can equate the LHS also. So in such a case, I can write MD upon CD will be equal to half MD upon FD. Now, what is CD exactly? If you see over here, CD is nothing but radius of curvature. So instead of CD, you can put R. So MD upon CD will be equal to half MD upon FD. CD is nothing but the radius of curvature. So MD upon the radius of curvature will be is equal to half MD. Now what is this FD? If you look over here, FD is nothing but focal length between principal focus and the pole. So over here, this is focal length will be represented like this. Now if you send MD towards this side, what will happen? MD upon R into, because it's in the numerator, it comes to denominator, MD is equal to half F. MD and MD could get cancelled. 1 by R is equal to 1 by 2F. So just take the inverse. R will be equal to 2F. Now you want focal length, right? So F is equal to R upon 2. This is how actually you can say that principal focus is the midpoint of this radius of curvature. Between C and D, the radius of curvature, principal focus will be the midpoint, because FD is nothing but half of R. The focal length is nothing but half of R. Now you might think that MD is there, but it's generally pole, right? It's nothing but you have just drawn a perpendicular, assuming this like MP as a straight line itself. Because when paraxial rays are there and then they are really near to the pole, then you can consider this as very small region. So instead of taking it as bent, you can consider it as straight line itself. So don't get confused saying that D is completely entirely different. CP only should be a radius of curvature, right? You can just think it as it's coinciding. D and P are coinciding and it is like a straight line because it's very small region that we are talking about. So this is how you will prove that focal length is half of radius of curvature, or they might ask prove that principal focus is the midpoint between C and P. So then you can do this derivation. Just remember, parallel through focus, draw the normal through center of curvature, then angle of incidence, angle of reflection. Remember Z, so it will be theta, and over here Z, it will be 2 theta. Consider the tan thetas and you will approximate them to theta, and then this 2 can be sent over here, so both the sides theta will be there, so you can equate both of these and just cancel out MD, and instead of FD put F, instead of CD put R, then you can get off this. Now mirror equation. So generally wherever all these reflected rays are meeting at a point, their image will be formed. Always remember, real image can be captured on a screen and real image will be always inverted. There is no real and erect image. Real image will be always inverted. Virtual image is where they're appearing to meet. So they will be behind the mirror because you won't be able to see that. And always virtual and erect. Virtual meaning erect. So it will be straight. So over here we are trying to get the mirror formula, the magnification. This is one more derivation. So let us see through this. So image is real if the rays actually converge at the point. So image is nothing but whenever these rays are going to meet at another point after reflection. So whenever the rays from a point actually meet at another point after reflection, that point will form the image. Many reflected rays are coming and meeting at a point, that will be called image. Real meaning if they're actually converging. But if it is virtual, they just appear to diverge from a point that is at the backward. Now, these are the certain rules that we have already seen. So if it is parallel, then it should pass through the principal focus, then the ray through the center of curvature will simply retrace that path only, and then the focus of concave mirror passing through, then yeah, if it is passing through the focus, then again it should become parallel, and at any angle at a pole it is forming, then this principal axis will act as a normal and it will come back following the angle of incidence and angle of reflection. However, the angle the incident ray has formed, like that only this angle should also form. These are the general ways. Generally, if you want to form image, minimum two incident rays are needed. 3 are also fine. Minimum 2 incident rays you can draw and show how they are converging. Their image should be formed. But in reality, actually many rays are coming. Don't think only 2 rays are there. If you're just putting light, many light rays will come. But we cannot just overcrowd the rays. It will be difficult for us to then interpret the image. So maximum 2 or 3 you can draw. Now you have to remember this also in 10th grade. Whenever the object is beyond C, the image will form between C and F. So first remember this. If the image is at infinity, it should form at principal focus. If the object is at principal focus, it should form at infinity. If the image is beyond C, it should form between C and F. If the image is between C and F, it should form beyond C. And if it is between F and P, that is the special case. Actually, it is given over here. So if the image is between F and P, this is the only scenario where virtual image is formed in case of concave mirror. And this is the only scenario where virtual image is getting magnified. Generally, convex mirror is where there is a virtual image and it is always diminished. But this is the only case in case of a concave mirror where virtual image is formed, and it's the only scenario in entire mirror saying that where virtually magnified is there. So generally in questions they won't directly give you this is a concave mirror, this is a convex mirror. You have to find certain clues. So if they say a virtual image is formed that is being magnified, you should be able to catch that it's a concave mirror, because in convex mirror also virtual image is formed but it's always diminished. So this is a special case when between F and P if the image is there. See, parallel through focus. Some angle at pole, with that angle only it is coming back. Now you're producing them. See, they have to meet at a point. Now if you see these are like just almost parallel. We know that if I'm going to produce this like towards the left side, they are not going to meet anywhere. So I started producing them. Back of the mirror also image can be formed. That is a possibility. So I'm producing and they met at a point. So as you can see, this is the object, this is the image. It is straight, so it is virtual and erect, and it is behind the mirror, that's why it's virtual, and it is being magnified. So these are the various cases you can remember so that you can draw this and tell where the image is exactly between F and P. The only case where it is forming virtual and magnified. If it's on F, it will be at infinity and it will be highly magnified. If it's between C and F, it will be forming beyond C and that will be magnified. If it's at C, it will form just that size only. Real inverted, real in every case is real inverted except between F and P. At C, same size will be there. It won't be magnified or it won't be diminished. And beyond C, if it's there, it will be between C and F and it is diminished. So remember these cases so that it will be easier to draw this image. So we can take a concave mirror, put an object beyond C, so it should form between C and F. If you know that, it will be easier to draw these rays. So parallel, then through focus. Some angle at pole, with that angle only it is coming back. Then through the center of curvature, it will go in that same path. These points, all the reflected rays are meeting. So wherever it's meeting, there only head should come. So it will be inverted and diminished. Now between principal focus and pole, the distance will be focal length. Between, this is the image. Between image and P, represented by V is the image distance. Between pole and the object, represented by U, that is the object distance. Now, so the proof goes like this. We have to consider two right angled triangles. So A dash, B dash, F and MPF, and they are similar triangles. So if you see over here, first with respect to principal focus, take the triangles. So A dash, B dash, F along with F, P and M. So you can draw this separately if you're getting confused. Let me take a new page. So the right angle triangles are like this. So this is our A dash, B dash and F, and one more triangle they told to take is M, P and F. Again, MP can be considered as a straight line because they are paraxial. If you want to write that statement, you can write down saying that they are paraxial rays. Very near the pole they might be there, and this will become a very small region. So you can consider it almost as a straight line. So don't get confused. This is like a curve. How can you consider it as a triangle? You can write that reason. Then triangle MPF is going to be like this. Compare with the image. You will be able to understand. MP and these are similar triangles. So if they are similar, we know that the ratio of the sides should be equal. So always take this triangle first. So A dash B dash by MP. A dash b dash a dash b dash by a dash b dash by mp. This will be equal to what? This should be equal to, then take the horizontal line. Take the straight line and the horizontal line, basically the 90-degree wherever it is there. So a dash b dash by mp, and the horizontal line, not the hypotenuse, would be bf upon fp. So it will be equal to b dash f upon this horizontal line fp. So this is what is written over here. They have considered two triangles and they have written this is what the similarity is. Now they have replaced PM with AB. Why? They're exactly parallel. Like you can see, their height is the same thing. They're exactly parallel. Their height is the same thing. So you can replace MP with AB. So it will become A dash B dash A dash by BA is equal to B dash F upon FP. Now we will take other sets of triangles also. Now with respect to P, you take ABP, then A dash B dash P. So we can draw those also. So again take the straight line part and the horizontal line. So the straight line part is nothing but B dash A dash by BA. B dash A dash by BA. Then take the horizontal line B dash P, this line, divided by BP. B dash P divided by BP. Now we know if you're going to compare this equation with this equation, what is happening? The LHS is same. So what can you do? You can equate the RHS. So you can say that B dash F by FP will be same as B dash P upon BP. This is what? B dash F upon FP is equal to B dash P upon BP. This only they have written in a certain format. So if you see, B dash F upon FP you're writing in this format, that is equal to B dash P upon BP. So B dash F is written like, B dash F is written like, if you take the entire B dash P, if you take the entire B dash P, this entire line, and subtract FP, you will be left with B dash F. So instead of B dash F, I can simply write B dash P minus FP. I'll get B dash F. So that's what they have written over here. Write B dash F as B dash P minus FP. FP will be the same thing, equal to this thing, B dash P upon BP. Now we will start writing what these are actually. So if you see, what is B dash P? B dash P is nothing but image distance. And remember left hand side, so it is nothing but negative. So negative V. B dash P is image distance, it is V. So negative V has to be written. Okay, negative V is written. Next thing is FP. What is FP? Okay, F and P, between principal focus and pole, we know it is focal length. Focal length, again it's left hand side, so it should become negative. Negative F should be written. Now they have actually negative F is given over here, they have multiplied it with this negative sign, so that's why it became positive over here. So this is negative V, negative F. So negative V, negative of negative F will become positive. It's like this, negative V, negative of negative F, divided by again FP only, so that will become negative F. So it will become negative V minus minus is plus, then F divided by negative F. That is what is written over here. Now this is equal to B dash P. What is B dash P? B dash P is again V, image distance, and that should be negative V. So negative V is written. Then it is BP. What is BP? B. AB is object, right? So BP, this is the object distance. Again left hand side, so negative, negative U. Negative V upon negative U. So now you can actually multiply this entire equation with negative symbol. You can do that. Left hand side also with negative sign you multiply, right hand side also, numerator also, denominator also, you have to multiply it with negative sign. So entire equation, if you're going to multiply with negative sign, what will happen? First multiply in numerator. So negative into negative, positive v. Negative into positive, negative f. Negative into negative became positive, so you got f. Negative into negative became positive, negative into negative became positive. So that is why we have obtained this equation. Simply write the opposite signs for everything. Here negative is there, meaning write here positive. Here positive is there, right, meaning write negative. Here negative is there, write positive. Negative is there, write positive. So basically if you're multiplying it with negative sign, the existing signs will change. This can be done. But if you're doing this, remember, for entire equation you have to do, not just one side, and for both numerator and denominator also you have to do. Now separate this, like v minus f divided by f is there. V minus f divided by f is equals to v upon u. So I can write this as v by v upon f minus f upon f is equal to v by u. I can write it in this manner. Because denominator is same, meaning I can just, again, if you're going to subtract v minus f by f only, you can write. Now f by f is what? 1. V upon f minus 1 is equal to v upon u. Now multiply entire equation by v, or just do into 1 by v for every single thing. 1 by v, if I do, v and v got cancelled. 1 by v, if I do, I can just write 1 by v. Here also 1 by v, if I do, here v and v got cancelled. So what is left over here? 1 upon f minus 1 upon v is equal to 1 upon u. Now this is nothing but our mirror formula. 1 upon f is equal to 1 upon u plus 1 upon v. Over here, yes. 1 upon f is equal to 1 upon v plus 1 upon u. Now for magnification, we are actually taking, you can take the second equation actually. So this is the second equation, as you can see, and just put the values from that image. Now b dash a dash, what is that? What is b dash a dash? Nothing but the height of the image. Height of the image, you can tell it as h dash. So h dash. This will be h dash. Then what will be ba? This is nothing but the object ab. So this is the height of the normal object. So this is h. So h dash upon h, but don't forget the sign because this is inverted. This is negative y-axis. You have to write minus h upon h. So you have to write, let me erase. You are writing minus h upon h because that was inverted. That was towards the negative y-axis is equal to what is there in the right hand side? B dash p. B dash p. Nothing but the image distance. So it will become negative v because it's towards the right. Negative v divided by, then it would have been bp. So bp is object distance. Again towards the left side it should be negative. So negative u. This negative symbol got cancelled out. You can send this negative sign over here. So it will basically be h dash. This is h dash because it's image distance by object distance should be equal to negative v upon u. This is nothing but gives you the magnification. Like how the size of image has changed with respect to object. Object size is this much, then image size is this much. So basically taking the ratio of their height, saying that okay, this much difference I got. This is how the image height changed. So that will be your magnification. So one thing to remember, for the case of real inverted image, if it is formed, then there is this proper sign convention. So whenever our magnification is positive, you will say that you can get a clue that it is virtual image. And whenever according to the sign convention, when magnification is negative, That will be real and inverted image. Why is that so? Because if it is real and inverted image, h dash, it will be inverted. If it is inverted, it's to the negative y-axis, here minus symbol will come off. Or if you use this formula also, it will be towards the left side. That means it will be negative. Both image distance and object distance will always be negative. Negative, negative cancel out. Still this negative sign is there. So if it is real and inverted, obviously this entire thing will become negative only. But if it is virtual image, generally virtual images are formed behind the mirror. That means towards the right. That means we will become positive. Object distance is always negative. Remember that. Because object will be always kept in front of the mirror. You cannot keep the object behind the mirror. So always it's towards the front of the mirror, always towards the left only you're measuring, so you will be negative. V is positive. This negative will get cancelled out. Overall you'll get positive. And if it's a virtual image, obviously object will be straight only. An image will not be inverted. It will be towards positive y-axis only. This will also be positive. So if it is entirely positive, you can directly say it's a virtual image. And this case I've already discussed. And over here, in case of a convex mirror, only two cases are there. One, it will be in infinity, that we have already seen previously. Parallel beam of light will be coming as if they're diverging from the focus. The reflected rays will be here. The image will form. It will be highly diminished and virtual and direct. But if it is not at infinity, anywhere, suppose here, anywhere it is there, same space between P and F only, image will form. So you can tell this is incident ray that is parallel. Through focus, reflected ray will come by smaller angles. If it is coming towards the pole, by that angle only it's getting reflected back, and you will basically draw the dotted lines to see where they are meeting. Because here though I am able to understand, if I'm just going to extend these also, they're never gonna meet. So extend them backwards, always between P and F only they will form. So that is it for today. We can solve these questions in the next class, and further there is topic refraction. We can cover it in the next few videos. Please like if you like the way of explanation, and feel free to leave any comments if you have any doubts, and please subscribe and share this video. Thank you guys. See you in the next video. Bye.